Welcome back to Practical PyTorch. In this video you'll learn where a tensor lives, on the CPU or the GPU. You'll learn how to move it with .to device. And you'll fix the one error almost every beginner hits. Let's start with something that should just work. We have two tensors. Both are fine and both hold two numbers. We add them, a plus b, and PyTorch stops with a runtime error. It expected all tensors on the same device, but it found two, CUDA 0 and CPU. Nothing is wrong with the shapes. The two tensors are just sitting in two different places. By the end of this video, you'll know exactly how to fix this. This video has 4 parts. First, every tensor has a device, and it is only ever on one. Second, crossing the boundary. .to, device is the door between the CPU and the GPU. Third, the mismatch error. Why two tensors on different devices refuse to touch. And fourth, code that runs anywhere. One line picks the device for you. Part 1. Every tensor has a device, and it is only ever on one. Your machine has two places to keep numbers. The first is the host, your CPU and its main memory, its RAM. The second is the device, the GPU with its own separate memory called VRAM. Think of them as two desks. Numbers on one desk are not on the other. When you make a new tensor, it starts here on the host. This one is called x. 2 words we'll use for the rest of the video. Host is the CPU side, and device is the GPU side. Every tensor carries its device with it, and you can just ask. First, we build a tensor x with 3 numbers. Then we print x.device. And it says CPU. There is a real NVIDIA GPU in this machine, and the tensor still starts on the host by default. .device is an attribute, just like .shape and .dtype from the tensor's video. Shape, dtype, and device are the 3 things to print before you debug anything. You'll see 3 of these device names. The first is CPU, the host. By default, a tensor starts here. The second is CUDA, an NVIDIA GPU. A machine can hold more than one, so PyTorch numbers them. The first one is CUDA 0. And the third is MPS, the GPU built into an Apple laptop. 2 lines tell you what is really in the machine. The first asks torch.cuda. Is available. The second asks torch.backends.mps. Is available. The answers come back true, then false. This machine is a rented GPU box with an NVIDIA card, so CUDA is true. It is not an Apple machine, so MPS is false. Ask, never assume. These are the exact same 2 lines, but now we run them on an Apple laptop instead of the GPU box. And the answers flip, false, then true. This machine has no NVIDIA card, so CUDA is false, but it does have an Apple GPU, so MPS is true. 2 machines made this video. Every console block on screen tells you which one printed it. Part 2. Crossing the boundary from the host to the device. To move x onto the device, you call one thing, x.to device. The 2 sides are joined by a bus, called PCIe. That is the road the numbers travel on. And now x is on the bus, in the middle of crossing over. One call and the numbers are copied across the bus. What that trip costs is a later video. For now, just watch it cross. The crossing finishes, and x arrives on the device side. It now sits in VRAM, the GPU's own memory. The the GPU can finally work on it. And notice, a faint copy is still back in RAM. Remember it, because the next two slides are about exactly that copy. Let's do the move for real. We write x equals x.to device, keeping the result back in x. Then we print x.device. And we print x itself. .device now says CUDA 0, and the tensor prints its home too. Device equals CUDA 0 right there in the tensor. A CPU tensor prints no device at all, so silence means CPU, and a name like CUDA 0 means the GPU. This part confuses a lot of people, so let's go slow. This is the new X sitting on the device. But the old X is still here in RAM, drawn with a dashed edge. .to did not empty the host, it made a second copy. So .to returns a brand new tensor on the new device, and leaves the old one behind. That is why you write x equals x.to device. Part 3. The error almost everyone hits. Now we have two tensors in two different places. Tensor A is on the host, and tensor B is on the device. Try to add them a plus B, and PyTorch refuses. The rule is simple. Every operand of one operation has to be on the same device. No exceptions. Let's make that happen in code. Tensor is two numbers and it stays on the host. Tensor B is two numbers, and we send it to the device with .to device. Then we add a plus B. And there is the runtime error. Expected all tensors to be on the same device, but found at least two devices, CUDA 0 and CPU. The message names both devices. Read them, and you already know which tensor got left behind. Let's line the two names up with the picture. The message said CUDA 0, that is B, over on the device. And it said CPU, that is still back on the host. So this is the debugging habit. The error already tells you which side each operand was on. You just have to read it. The fix is one move. Send the tensor that is behind. We write a equals a dot to device. Then we add a plus B and print the device of the result. And it says CUDA 0, it ran. Both operands are on the device now, so the result is on the device too. Move the operand, not the operation. Part 4. Writing code that runs anywhere on any machine. Don't type CUDA in 20 places. Pick it once. Device equals CUDA if torch.CUDA is available, else CPU. Then every move just uses that one name, x.to device and y.to device. On an NVIDIA machine, this is CUDA. On a machine without an NVIDIA GPU, it is CPU, and the very same script still runs. Let's run that line on the GPU box and see what it chose. Same line as before, device equals CUDA if available, else CPU. Then we print device. And the string is CUDA. The card is there, the test came back true, so it picked CUDA. One string chosen once, used everywhere. That string is what every dot to below it will get. Add one branch and the same script uses the Apple GPU. Try CUDA first, then MPS, and if neither is there, fall back to CPU. Then we print device. On the laptop, the string is MPS, order matters here. The first test that is true wins, so we ask for CUDA first. Same file, no edit. The machine answers for itself, and here the answer is MPS. A model moves too. We build a tiny one, nn.linear, 3 in and 2 out. Then we call model.to device. And look, there is no assignment on this line. We print the device of its first parameter. And it says CUDA 0. The model moved even with no assignment. A model moves itself in place. A tensor does not, and that difference is exactly what the next slide is about. Your turn, we make x with torch.random3, then on its own line x.to device. Then we print x.device. What does it print? Pause and guess. Okay, here it is. It prints CPU. Dot to handed back a new tensor and nobody kept it, so x itself never moved. Let's run it and confirm. We build x with 3 numbers on the host. We call x.to device, but we don't keep the result. Then we print x.device. And it says CPU. The GPU is right there, the call ran, and x is still on the host. Model.to moves in place. Tensor.to does not. The fix is 2 characters. Put x equals in front of it. Let's recap. Every tensor is on one device, and you can always ask with x.device. Every operand of one operation has to be on the same device. Put 2 devices in one operation, and PyTorch stops with a mismatch error. .to is the only door and it copies, so write x equals x.to device. And pick the device once at the top in one line. So now you can put a tensor exactly where you want it. Next, we look at what PyTorch quietly remembers about it. PyTorch can record what you do to a tensor, then play it backwards to compute the derivatives. That's AutoGrad, and it's the next video.